Great. Hello, my name is Cecily, and I'm going to be talking about plume surface interactions on the moon, and more specifically, what happens to the dust underneath the lander as we approach the surface. So this is work that I'm doing with Christine Hartzell and Parvati Prem. And as you could see, some other people in the room are using the information as well. As we've already established, dust is one of the greatest challenges that we're going to face when we go back to the moon. What I show here is a video from the Apollo 11 landing showing the dust curtains that are spraying as we approach the surface. And when you listen to the audio of this video, you hear the astronauts say that this starts to get kicked up at about a 40-foot altitude above the surface. Now, of course, there's issues with the dust potentially damaging our equipment and how far it could travel and possibly deposit onto other surfaces. So we're worried about that. But from a scientific perspective, it's also very interesting because, as Michael mentioned earlier, there is a very small crater that formed under the lander that was excavated when it landed. And this is related to the properties of the regolith itself. So when we're studying these plume surface interactions, we could look at this from both an engineering and a scientific perspective. So we're using the Monte Carlo method to simulate the dust plume interaction. And this is work that was started by somebody named Aaron Morris in 2012. He integrated this dust gas coupling into a DSMC code that Parvati Prem is using. And if anybody caught her talk, she gave some results from that yesterday. And what we did is we picked up this code, we're reintegrating the dust coupling into the code, and then we're using that to look at what happens when we land with different size landers at different landing locations, and looking at the full descent path of a lander as opposed to just hovering at different altitudes, which is generally what most people do. And we're interested in things like the ejecta of the dust underneath a lander, how far the dust is traveling at what velocity, stuff like this. So to create our gas molecules in our simulations, we're not accounting for the actual nozzle geometry, but instead we're using this analytic solution here where we insert dust into the simulations as a function of their distance from the nozzle exit. So we use this relationship from Roberts 1966 to calculate the density, the velocity, the temperature of the gas. We place that into the simulation, and then we let the DSMC method let the gas plume expand. And then for the dust, we're using an empirical scaling relationship that was developed by Phil Metzer's group at Florida. And this is through a set of plume impingement experiments that showed that the erosion rate underneath a plume is actually proportional to a Froude relationship where you have, which is a relationship between the aerodynamic forces and the gravity in a system. And what Aaron Morris did is he took that proportionality and he applied a scaling based on observations from Apollo. So he found that if you multiply this proportionality by 0.0025, then that accounts for the amount of mass that was eroded underneath the Apollo lander. What we do is at each step in our simulation, we sample the density of the gas right above the surface. We determine how many dust particles we have to inject into the system based on this relationship. And then we let the DSMC method handle the coupling between the gas and the dust. So I will present just some quick preliminary results that we have from two different types of landers. We have the Chang'e 3 lander and an Apollo type lander. And just to point out, a key difference between the two is the diameter of the nozzle and the thrust of each of the landers, where the Chang'e 3 lander is a much smaller nozzle diameter and lower thrust. So what I'm showing here is the entire descent of the Chang'e 3 lander based on the trajectory that was reported in a publication giving the descent path and the velocity. On the right-hand side, I show the number density of the gas molecules that are in the simulation. And on the left side, I show the number density of the dust particles in the simulation. And the gray that's overlaid in the left is just to show you where the gas is here. I'm going to switch to the next one, and we could just continue to watch that again. This is the Apollo lander. And so a few key things I want to point out here, without flipping back and forth, the number density of both the gas and the dust is much higher in the Apollo case, as we would expect. But if we watch this video, we see that we have the shock layer forming at the bottom, and that as we descend, it's moving closer and closer to the nozzle axis. And so that's indicating that as we descend, the erosion is moving closer to the nozzle axis as well. And then on the left-hand side, the dust, as we go down, we're going to see that the dust curtain is moving upwards at a steeper angle. And then whenever the gas, we turn off our engine here, we still have the dust that's ejected, lofting, and then falling back down to the surface. As I mentioned before, we were using this empirical scaling relationship. So now I'm just showing the velocity of the gas molecules at a specific 5-meter hovering height. And if we look at the entire time lapse of that simulation, we could see how the erosion profile changes as a function to the distance to the center of the nozzle. So the top plot here is showing the erosion rate by distance from the center nozzle for different hovering altitudes. So the highest peak there is at an altitude, I think can't remember if it's 3 or 5 meters from the surface, but it gives you an idea of the magnitude as we move closer, how the erosion is increasing. And then if we look at the erosion rate for the entire descent compared for the Chang'e 3 and the Apollo landers, we see it's about twice as much for the Apollo lander. A few other things that we could look at that are quite interesting are the interaction between the dust and the gas. So here I'm showing the number density of the gas molecules, where on the right, we have a coupling with 1 micron dust particles, and on the left with larger 10 micron particles. And so you could see here that in the left-hand side, we have this blip that's right at the bottom of the plume. And this is really the effect of the dust on the gas plume itself. And we could see that when we look at the location of the dust. So on the left-hand side, we have that ejecta curtain of the 10 micron dust particles, and then on the right of the 1 micron. So even though we see that there's a lower number density of the 10 micron particles, they're having a much greater effect with their larger mass on the plume itself. A few other differences to point out are the smaller particles have a steeper ejection angle than the larger particles, which is consistent with other simulations and what we would expect as well. So finally, just a few comments on the velocity of this dust. Here I'm showing the velocity of the dust, 1 micron dust particles for the Chang'e 3 and the Apollo landers. And the color here is the dust velocity. And so we see the ejecta curtain is more or less the same, but the velocity of the particles is quite different and much higher in the Apollo case. So we're getting speeds of about 500, 600 meters per second in this Apollo simulation. And if you look at the ballistic trajectory of those particles, and actually Aaron Morris performed another simulation where he patched out and looked at the far field dust spray, these particles could actually travel hundreds of kilometers. So Aaron found that you had dust deposited as high as 300 kilometers from the actual site of the landing itself. So just a few last comments on where we're headed with this. We are looking at revising, still modifying a few things in the code. So as I mentioned, we have that analytic solution for how we're introducing the plume molecules. We are going to consider other ways of doing that that might be more realistic to the nozzle geometry. Also looking into different erosion models. The ones we were looking at were based on Apollo data, and now we have this a whole range of the Chang'e 3 landings that have done a lot of work on different erosion models as well. So we could input those. And then also we want to look at what happens whenever we consider different types of interactions between the dust and the surface, or dust and walls. And then in terms of analysis, after we validate the code with some experimental results, we're just going to take a more qualitative or quantitative look at the results that I just presented. So thank you very much.
We have time for a question. If anybody has some. All right, in interest of time, well, I might ask a quick question. So in your modeling, you have the examples of the 10 micron and the 1 micron grains. Do you have models that have both, or currently they're just the individual ones, or is it using both those populations?
So Aaron Morris did work with the entire distribution of particles based on lunar regolith. The code can do that. I haven't personally run those simulations.
That's in the TBD.
Yeah.
Okay, awesome, thanks.